So I'm actually going to sit down for this because I'm going to try to control the controller at the same time as I'm doing everything else. And so this is kind of an experiment for me. I've never actually done like there's no slides, and I'm going to just try doing everything live. So once in a while, I expect something to crash, but since with the magic of instant recompile and rerun, it doesn't really matter. So let's begin. So I'm going to start at the beginning of my journey in 3D, which is basically, I always think of things like from first principles. And so one of the first things I look at is I look at anti-aliasing, and I look at like reconstruction quality of like an image. And so one of the first places that's really good to look at is basically let's just look at the difference between rendering fonts and rendering video. And then we can predict from this what we're going to need in terms of filtering. So let's begin. It's just a signed distance field font render, and the font is very basic. And what I'm rendering is I'm rendering at a virtual resolution of about a quarter of the screen resolution. And so there's at 1080p, there's only roughly 200 some lines. And then on top of that, I'm just applying like a Trinitron television post filter. Because if I was to show this at that really low resolution, it would look pretty awful. And so if we use the magic of like old displays, we can make it look pretty decent. This is the live part. Sorry. I don't normally type that bad. Oops. Okay, so the first thing I'm going to show here is I'm going to take the font down, and I'm going to run the font so it's basically pixel aligned. And so what you'll see here is now I have like a screen that's just filled with a bunch of characters, and the characters are actually designed such that on a really low-res screen, all the horizontal and vertical lines are basically snapped to a pixel grid. So effectively, we have perfect hinting by font design. And then now we're going to look at, so another thing I should point out here is the blurriness you're seeing is from like the CRT filter that's applied. So it's basically like the idea is that when the scan goes across the screen, it actually has like a footprint. It's not just an infinitesimal dot. And now we're going to look at what this looks like in motion. Sorry, it takes a while, unfortunately. So this pattern's actually moving roughly at, it's moving at a subpixel rate every frame. And it's basically showing the problem of when we evaluate and we basically render it, it's getting the screen door effect. So what you're seeing here is if I go to maximum sharpness on the CRT, or simulated CRT, and then I move stuff around, I can't actually get enough precision in terms of like the phase difference between pixels, so that you can't see continuous motion. However, if I change the filter kernel width, and I go to something that's, a little bit wider from a filter kernel, but now we're going to be a little bit more blurry. Now I can scroll this on the screen, and hopefully that's working. Yeah. You'll see that you don't actually notice the pulsing sensation of like the text coming in and out of the frame. And so the point here is that if you're working in filtering, you might have to change like your evaluation criteria for sharpness when you're thinking about anti-aliasing for video versus just rendering text and where the text is pixel aligned. All right, so the next thing I'm going to do is we're going to start looking at some signed distance field rendering, or I like to call it digital origami, because basically we're just folding space in a distance estimation function. And then I'm going to start building up a process of looking at filtering in in that domain. All right, so this is just a dummy sign distance function. It's very simple, domain distortion with a bunch of lines, and the graphics is being rendered with just very basic. I'm adding some fog where something gets too bright when it gets close to you, and otherwise the coloring is there's no lights. It's just being colored based on world space position. And the reason I did this is because I wanted to show worst case aliasing. So if we look at the distance out here and we move around, this thing basically aliases like mad. And so this is a good way of working on first principles and figure out what do we need to do to make this a stable image. And the other thing I'm doing here is kind of like the other example. I decided I don't want to render at I don't want to render full res, because if I render full res, it'll be harder to see the artifacts, and it's a much simpler problem. So what we're going to do is we're going to work with half res. But now I'm running the reconstruction at full resolution. So the input is, so for every 2 by 2 pixels, I'm doing a ray march. And then I take the resulting ray march of the whole screen, and then I run some resolve on that and produce the full res. And so the first one's effectively nearest neighbor. Or, well, actually, I think that's bilinear. But let's go to, so the next change I have in here is I just did like a Gaussian filter kernel, and I used the same sample positions I had last time, so it's just on a regular grid. And so this will cut out some of the high frequency noise, but as you can see under motion, it's still not very good. The other thing is I'm doing all the filtering in linear, and so when things overexpose, for instance, on these, you might actually see, you can start to see some problems with where it basically looks really low res on the edges, because those are brighter than the screen, and if you convolve that kernel, you're going to get a result that's still brighter than the screen. So I'm not doing any tone mapping or anything on here. All right, so the next thing we could try, which you might not have noticed the difference because there really isn't that much, is we can start using like a stratified pattern for the samples. And so what I did here is I took the sample positions, and first I arranged them in like a honeycomb pattern, which is a better packing than a regular grid. And then I basically randomly permuted the honeycomb pattern in a direction offset, in a random direction away from the center. And then I run some like relaxation algorithm to basically remove the clumps. And so it's not the perfect sample distribution, but it's pretty decent. And at the same time, it kind of breaks up a little bit of the problems we're getting in the like vertical and horizontal areas, but it's not enough to make much of a difference. All right, so now we're going to look at some temporal filtering. So what you're looking at now is you're looking at the same type of thing you had before, same resolution, same input as the previous frame, except for now the pixel positions we're shooting the rays out are actually, they're jittered every frame. And the way I do the jittering is I'm just offsetting where I go in my little pattern of sample positions. And so now you basically lose a lot of the problems you had before, like this starts to look like a pretty decent image in motion. And again, we're not rendering full res, we're only rendering half res, and the undersampling artifacts are not as bad. And so what I mean by temporal filtering is, what I do is for every ray I shoot, once I hit a surface, I go and I figure out where I was in the previous frame, and then I pick that color. And so when I write out color for a ray, I write out two colors. I'm writing out the color for this frame and the color in my accumulation. And then I take all those and I basically do the reconstruction again, but instead of having one color per pixel, I now have two. And so I can use that in my reconstruction filter. And so the reconstruction filter in this case is a very simple one. It's basically I just take the Gaussian, I convolve with the Gaussian, like the second example. And then I add in another multiplier, and that is a multiplier that tries to reduce the noise. And so the multiplier in this case, I'm just going to try to bring it up on the screen. Now, you might not be able to read this, so it's this multiplier here. I'm guessing nobody can read that, so I'll read it. Basically, what I'm doing is I'm taking the difference between the reprojected value and the current frame. And so that's like the difference. I multiply that times a constant, a pretty large number in this case. And then I add 1 to that, and then I take the reciprocal. And so what that does is as that difference increases, so I basically see a large difference between frames, it starts reducing the weight of the sample in the kernel. And so this is it's a very biased function. So if we were to look at it again and I toggle it on and off, what you'd see it basically erode away some of the bright areas, which is not what you want. Okay, let me reset that. Okay, so we're back in our example again, and there's something we can do beyond this with temporal filtering. We can start, since we're doing a reconstruction and we actually don't have high frequency detail at the full screen res, we can start adding stuff in there to basically hide the patterns that we would get in. So we can add something like this. This is basically, I'm applying something that does a screen distortion, something that adds some like depth of field, but it's not depth of field, it's just on the edge of the screen. It increases and acts like there's depth of field, or sorry, acts like it's out of focus. And then I'm adding a noise back in. And so this, I'm actually adding full pixel noise. And the idea here is like, if you're at night and you open your eyes and you've adjusted to the night, you don't see a regular picture, you see something with a lot of noise, right? And so the idea is, what I want to do is I want to take advantage of what we're naturally expecting to see when image quality degrades. And so the idea is that I can throw noise on here, and it's actually going to become more believable because it's hiding artifacts. The other thing I like to do is go in and actually use something like an old CRT filter. And CRT filter, like a shadow mask or an aperture grill, does a really good job of basically hiding the fact that you're missing full resolution. Okay, so why don't we look at something more complicated? All right, so this is another scene, and I produced this scene. It's a very simple fractal, a little bit more complicated than the last one. But the idea was to produce a scene that basically had an extremely large dynamic range. And so I want to actually look at the problems that we get visually when we're dealing with the scene where the brightness goes extremely bright. And this is normally a real big problem for something like filtering, in that the other thing is I'm not running a tone mapper on here. So I'm just allowing stuff to clip, which maybe isn't the best idea if you were actually producing something, but for this example, it'll work. And so one of the problems before was that the last temporal filter had an extreme bias on it. And so I'm going to bring that one back up. Okay, so the difference between these two, one of them is basically super biased, the other one is not. And so the advantage of the super biased one is it basically gets rid of all the bright stuff in the scene, so that if the bright stuff flickers, you don't really notice it. The problem is that under motion, it starts thinking it has like a continuous line, and so you're seeing the bias under motion, which is pretty bad. Another thing that's the disadvantage of having biased filtering is that one thing you're expecting to see with a really bright light source is you expect to see some amount of blooming. And so if your filter kernel is highly biased, that'll go away. And so if I change this, now you're actually starting to see the blooming again. So if you have a really bright point on the screen, you expect it to like expand outward a little bit. And so we're actually seeing that in this one. So another thing about this tracing is that I'm basically doing all the tracing per pixel. And so if I was to like, well, let's go down. I'm trying to find a place where I can show something. Sorry. Let's see. How about in here? So you might not notice this, but I have a lot in here, which as you get close to something, the detail kind of expands. And as you get far away, the features widen. And the reason why I did that is because I wanted to do this in real time. And if I basically shoot the rays and I hit everything perfectly, I run out of time. The frame, I can't get the frame rate. And so one way to deal with that is basically to put in some LOD. And the way you would normally do LOD in like a triangle scene is you'd have another model, and that model would be like a simplified model. And the equivalent LOD for like a signed distance field is kind of like what you do is you terminate the ray early, and you falsely hit something when you get, like I could be shooting a ray over my monitor here, and I didn't touch the monitor, but I got within a threshold. And what I do is, as the ray keeps on marching along, when it starts getting like it's taking too much time, I increase the threshold, and that basically widens the surface. And so this becomes a problem because if I start moving close to something, it can actually modify the background, because if you're looking at the background there in the center, well, actually, see, I don't have a laser pointer, but you can start seeing things in the background being modified because of the foreground, because the ray took too long to traverse there. And so that's something we want to avoid. So getting back to the temporal A for a bit, so the primary goal of the temporal A is basically to remove noise in this, because we already have a really good sample pattern. We don't really have to worry about the traditional problems of anti-aliasing, which is, well, the fact that we're going to have, actually, why don't I just show you what it looks like with nothing on. So there's your input signal. That's with no jitter, no nothing. This is what like a traditional renderer might actually show. And so the difference is quite striking. Like this, to me, looks really horrible, and like my eyes start bleeding, when I start looking at this. And so if we put on temporal A again, and we add a little bit of the bloom back in. Oh, and the other thing I have here is like a scanline filter. Again, it's like another CRT-inspired post-process. And so this particular example, again, the primary point of the temporal filtering is to get rid of the noise. And so the actual filter that I'm using in this one is this last line down here, which is the better column. And so the new filter, it's the same type of style as before. We're just weighting samples. And so in this one, I take the difference between the previous and the current frame. And oh, actually, there's one big, huge thing I forgot to talk about. The temporal filter also has a neighborhood clamp, and that's the reason why this thing works. And so when you do the reprojection of the prior frame into the new frame, and you're getting that second value that you're feeding back, sometimes that reprojection is going to be false. And the way you figure out that, if you want it to work in a robust way, is you basically look at the current frame and the samples surrounding the pixel, and you come up with some threshold of like a minimum and a maximum. And then you take the old feedback, and then you say, well, I'm going to clamp that to the minimum and maximum. And so that's one way of doing it. There's other ways, like you could do something more advanced, like pattern matching, where you basically check a larger pattern than just the neighborhood. But I'm doing something simple because I want it to run really fast. And so going back to that equation in this one, I'm looking at, I take the difference between the current and the feedback, and then I divide that, in this case, by the maximum of the current and the feedback. And the idea here is that I want to make it so it's not biased, so that if I have a really bright thing and then I have a really dark area, that those things have, locally, those things have similar weights. And so if I take the difference between the feedback and the current, divided by the maximum of the brightness, and then I have some minimum so it doesn't go, divide by 0. And then I take 1 minus that value. Now I have a value between 0 and 1. And so at 0, you're not seeing much of a difference. At 1, you're seeing a tremendous difference. And then I square that, and the idea is to basically cause the noise to progressively get reduced as the change gets progressively higher. All right, so now we're going to go to another example. All right, so I just changed this a few minutes ago, so I hope I can find something interesting in here. But let's see if I can go somewhere that has something interesting. This is the problem of not actually having a map. So there's no map here. It's just basically an infinite thing you can fly around in. Okay, so why don't we just sit here for now? So in this one, I decided to tackle the next big problem, which is we were working with half-res source material the whole time, and now I want something that's effectively full res, and I want something that basically has spatial information visually that has, like a phase between as the geometry moves between pixel to pixel. I want it to have the full res detail. And so the other thing I don't want to do in this is I don't want to deal with the fact that, well, I have to shoot every ray for every pixel or for many samples per pixel, because if I was to do that, again, we'd come back to that performance problem that nobody wants to have to solve. So I'm going to go to my notes really quick so I can actually go through the details of what we're doing here. So in order to get the filtering high quality, what I do is I still render at the quarter area, but I'm going to use the full reconstruction as to source my feedback for the temporal filtering. So before, what I was doing is I was running temporal filtering at the half resolution or the quarter area, and then I was doing a reconstruction filter that would basically try to upsample. And so in this case, I'm still doing the upsample from this quarter resolution set of samples, but what I'm doing is now I'm actually going to pull the feedback from the full reconstruction. And what this does is it solves a few different problems. The first thing is that I basically have a history that's full resolution. What I don't have the input when I'm doing my reconstruction at full resolution. So I'm going to lose a little bit of information there. But the end result that I get out here is I get something that effectively is kind of shaded at half res, but it has, it's effectively kind of like having coverage samples or MSAA, but it works quite well. So another thing here is I'm not trying to solve the performance problem yet with shooting this many rays. And so I still have the same artifacts. If I was to find a good place to show you, well, that's probably just bloom, but you can start seeing, if you look at the middle ground in the background there, you're going to see things changing based on the same problem we had before, which is I'm doing my level of detail based on how long the ray is taken to travel. And so the size of things, changes based on how expensive it gets. And so what we really like to do next is we'd like to solve that problem. And that's where things become really interesting. All right, so this is a similar scene with a similar fractal, and it's a very, very simple fractal. I just reconfigured it a little bit. The difference between what you're seeing here and what you saw before, besides just the scene change, is that now I'm rendering and I'm going to the point where every ray terminates. And I'm doing it much faster than I was doing before. And so instead of working for every pixel and going and searching for the end of where the ray terminates, now I'm actually going and I'm doing a hierarchical trace. So let's see, we'll just leave it there for now. So the larger problem with doing a hierarchical trace is the fact that, and let me define the hierarchical trace really quick. So what I'm doing is I start with a really, really, really small resolution display, and I basically trace that display. And I go to where the ray gets close enough to the point where it's within the size of the pixel of that display. And so that's basically like the first level of the hierarchy. And then the next one, I would do a display that's twice as big, or twice as many pixels. And I would continue going until the ray terminates, and then keep on doing that. And so if I was to actually do that, and say I wanted to start with a really, really small display, I couldn't fill the GPU in the first pass. And so that's one of the first problems we have to solve. The other thing we have to solve is that ray traversal typically is not consistent across pixels. And so what I don't want here is I don't want each ray to be mapped directly to an invocation in my shader. Instead, what I want is I want my invocations to run at a constant rate. So basically, I would choose a fixed number of steps to traverse, and then I would basically map the rays to the invocation as that process goes. So each shader invocation might actually trace a few rays. And the idea is you just launch enough rays to fill the machine maybe 2 or 3 times. And then I'm using this, let me go up here and actually highlight it. So the new traversal algorithm is basically this section. Of course, this is text, not code. But the idea is that the shader, in this case, fetches a ray. So I just basically start on a ray. And then I run a loop for a fixed number of iterations. And so the iteration will do the distance estimation function. Then it'll run forward, walk forward in the ray. And it's going to check if the new position, well, actually, I think walk forward happens in the reverse. I think I wrote this wrong. But the idea is we'll check if the ray is close enough to the surface. If it is, we're going to store the result of where the ray, so basically just store the z value. And then we're going to start a new ray. And then we're going to keep on going in this loop that's basically doing distance estimation and traveling in a path. So one invocation in the shader might actually process a few rays. And so that is a really nice way to, it's a really nice place to get to because I'm limiting my occupancy problem to basically just this if the ray hit, let's store the result of z, and then let's fetch another ray. And so all the math is basically fully saturated. So the next problem is, well, how do we solve the traversal problem? Because if I have, maybe I have, say, 10 levels in my hierarchy that I'm traversing, basically a really large cone, and then smaller cones, and then smaller cones, and smaller cones. And so what I don't want to do is I don't want to launch that kernel and have that kernel basically not fill up the GPU and then waste a lot of time. Instead, what I want to do is I want to actually run one kernel that traces everything. And I don't want to have to deal with synchronization problems. And so the idea here is that when we're working on like a massively parallel machine, we can do something where, in certain cases, if data's not ready, we just recompute it on the fly. And so with traversal, I have this idea of breadcrumbs, where the larger cones will store their result, and then the new cones will just go and look at the result of the parent. And if the parent had actually completed and wrote a result, i.e. my z is not 0, it's actually ahead, I'm just going to start where that parent value was. And if the parent didn't finish yet, then I'm just not even going to worry about it. I'm just going to start at the beginning. And so if you order your rays at the top of the hierarchy first, or at the root of the hierarchy, and now you basically have a case where typically on the GPU you can see that the children nodes are actually picking up the results of the parent, and we're actually getting one kernel that can trace in a tree structure. So another thing here is I really wanted to do a trace that has a fixed cost, because my eventual target for all this, this is one of my just hobby projects for fun, was basically to start doing all this stuff in VR. And so in VR, you want a fixed cost per frame. And I think in general, even outside of VR, a fixed cost really has a tremendous benefit. So what I'm going to do is I'm going to take the last pass where I'm doing the most rays with the smallest cones, and I'm going to order the rays in that cone, I'm going to order the rays in that pass for each tile of the pass. So when I say tile, I'm basically taking a group of 4x4 arrays, kind of like a packet arrays. But I'm not going to run the packet altogether because I'm not worried about memory coherency on this. I'm actually worried more about computational efficiency because my distance estimation function is all math. And so what I do is basically this, well, I'll just highlight it here. I start with each tile, I start in one position, and then I start tracing the rays for every tile in the first position. I trace all those rays first. And then the next position in the tile, I trace all those rays. And so the rays in the rays I launch in the tile, I basically trace them in a random order every frame. And so what this means is the last level in the hierarchy, all the leaf nodes, that's the most dense part of the traversal. It's basically the point of where you're doing the most rays. And so if I have only one ray per tile per frame, that would be like the worst case scene, right? Or maybe on a less complex scene, I might actually get time to trace all the rays in the tile per frame. And so I can keep a fixed cost, but now I have a new problem, which is I need to start filling holes, right? Because not all my rays are actually going to terminate. But the nice thing is, since I did a hierarchical trace, the hole filling actually is pretty simple. Because at worst, I have the parent. And the parent is basically like a lower res version of the scene. And so I can use either the parent, or if the ray doesn't terminate, but I run out of invocations in the shader, I can basically say that the ray didn't hit its destination, but here's where it ended up before it hit the destination. And then in the hole filling pass, what I do is I look at the neighborhood rays, and I find a ray that seems to match the nearest one that's at least farther along than either the parent or the the ray itself, if it terminated early. It didn't terminate early, if the shader terminated early before the ray finished. And then what I get is I get a depth value for each. So basically I reconstruct full resolution depth, where at this stage I'm reconstructing quarter resolution depth, or quarter area, but half width and half height. And then I do a reprojection for every hole. I basically use that depth, and then I take that depth and I reproject where that pixel would be in the previous frame. And if I find a pixel in the previous frame, then I have potentially a real depth to work with. And I have to take the real depth and bring it back. And then I have to do a check really quick to see if the depth seems reasonable or not. And if it does, then basically I'm taking whatever holes I had in the scene, I refill it with whatever I had in the history. And so what I end up with here is I end up with a way of actually accepting a tremendous amount of loss in the scene. And so if the frame time becomes really expensive to trace the scene, I have a lot of holes, and it'll just gracefully degrade a little bit in terms of noise. But most of the time you don't see it. And so what I'm doing in terms of the shading is I'm always shading at full res, because the shading cost in mine, my example is basically I'm not doing any real complicated shading. I'm just doing something that's very ambient. And so the result of all this is a giant white screen. All right, so we'll start again. So the result is that I can basically trace a scene like this on this machine, and my fan hasn't even started up, which is pretty scary. So on this laptop, this is a 3 teraflop laptop, so it's decently fast. But at the same time, this demonstration is actually designed for going over 120 hertz. And so I think the full trace of this scene, it's 1.8 milliseconds. So it's, yeah. So let me show you some other stuff about this scene. So the first thing I'm going to do is I'm going to turn off the filtering again, and I'll just show you what it looked like. So this is actually what I'm shading every frame. So this should look like a pretty aliased. Well, actually, there's some jitter, which I turned off also, but this would be what you'd normally get if you were not to think about filtering, so, and you just shoot just a ray. And so it gets pretty jittery. And I already, by the definition of the scene, I actually try to keep it low contrast to remove the jitter, or sorry, remove the, like the temporal aliasing as much as possible. So we could turn we could turn it back on for comparison. Actually, I cheated. I did something else. Let me turn that back on. So now we're back in the full res version with the filtering. And again, I'm using an idea that if I have artifacts in the scene, I'm going to go after trying to solve the artifacts in a way that's very natural to what we expect from, our primitive lizard brain if like we're looking at night or we can't see something clearly. And so I'm going to put some noise on the screen. So this thing has a bit of noise, but it also has some, you still see some of the jittering artifacts, and I just leave that in there because I still think that's a little bit better than dealing with other problems such as aliasing. So another thing on here is I can actually show what this looks like with the fog turned off, and it's kind of showing, it's like peeking under the covers and realizing that the whole thing's a sham. So the lighting, I basically use a very simple method for just computing the lighting based on signed distance fields. And so I think I do like 15 steps in 2 directions. So I get like a front light direction and a previous, and I get a shadowing term by stepping out and actually at each of those points actually doing distance estimation, seeing how far away from something I am. And I would need to do a whole lot more in a scene that has this amount of space. And in order to actually get around that problem, I basically just decide that I'm not going to actually compute lighting correctly for anything that's really far away, and I'm going to basically use the fog to hide all that. And so part of the fog, I have 2 components, an in-scattering and an extinction. And so the extinction basically is the part that's pulling the lighting out of the scene effectively. And so I just set the extinction so the stuff in the background, you're not actually seeing it. So the lighting in the background there looks totally busted. But the lighting in the foreground, if I go, for instance, in here, well, it's a little bit more believable. And one thing I want to put, the reason I bring this up is because now you have no sense of depth, which is great. And then you can actually see that I'm actually tracing all these rays down to their destination. And you can also see that I have some artifacts which I left in the distance. You can start seeing some of the noise from me not actually. I'm basically doing an optimization as things get far out to not actually get the surface 100% correct, and so that's why you see some of the patterns in the background. But on the foreground stuff, I make sure I get close enough to the point where it works out well. And so if I look at traditionally complicated scenes where I have a lot of foreground occlusion, so you might have seen there some of the noise from when it got very expensive and it ran out of time. But it's very hard to tell in the general case. All right, so now I'm going to go to another topic in terms of filtering instead of optimization. So I'm throwing another scene up here, but this time instead of doing like a rectangular projection that you're used to seeing, I'm throwing in I'm basically throwing in a projection that is a spherical fisheye, so you can see all the way around. And I'm using this as like a worst case of distortion because it really is a worst case of distortion. And in order to render this scene, instead of doing what you would do, you would just render the rays and just shoot the rays in the scene, because you can do that, I wanted to actually create a problem that typically doesn't exist for ray tracing, which is I'm rendering the scene into a flattened octahedron. And so I'm simulating the problem you have, say, with with regular triangle rendering when you want to render for something like Oculus, or a VR that has a display distortion in the head-mounted display. And then basically to use this as an example of a way of showing better filtering quality. And I actually didn't do a great job of this because I kind of just put this together in a very short amount of time, but it does show some of the first principles. And so the idea here is I render into an octahedron, which you could think is kind of like an 8-sided dice, and that's flattened into basically a square, so you're seeing both sides. And then I take that octahedron, and that's my collection of samples, and then I render the scene over here. And so what the source actually looks like, if I turn the filtering off, is something like, I accidentally turned off more in the filtering, but so you can see some areas have basically a lot of undersampling, like the sides of the screen, the bottom, and so on. And that's due to the fact that I'm not rendering, I'm not shooting rays in the distribution I should shoot them in. We go back to the filtered. And so in order to make this image have the same filtering quality as before, what I do, every time I shoot a ray out, I record its transformed or its distorted position on the output display. So I basically have an XY position on the screen for every ray in the octahedron. And then when I'm doing my filter, my reconstruction filter, I'm just using that in the reconstruction filter as the distance between the center of the pixel and a sample. And so, sorry, I take the actual difference between the center of the pixel and the location on the screen. And so the filter kernel basically, for every pixel it has to do in the reconstruction, it goes and it samples from the nearest pixel in the flattened octahedron, and then it grabs the neighborhood of samples around that. And then it basically takes all those samples, looks at the difference between the sample position on the screen of where it's going to end up, and then the center of the pixel, it uses that distance for the filter kernel. And so one of the other problems here is that if you do this, you basically need a filter kernel that adapts to the screen based on the amount of distortion. And as a first example here, which is really a bad way of doing it, I basically just changed the filter kernel size, or the way I weight the samples, based on the distance away from how much distortion I have on my fisheye. So as the fisheye gets more distorted, I put in a factor that increases the size of the Gaussian filter effectively. But I'm not actually fetching different samples. I keep the pattern of samples I fetch relatively consistent, other than the fact that the flattened octahedron, you have to deal with edge and boundary conditions. And so a better way of doing that, which I didn't have time, would be to actually go and take the Gaussian filter and actually align one of the primary axes, like the x-axis of the Gaussian filter, to basically the direction of highest distortion in your screen, and then just do a different scaling for the x and the y. So you end up with an ellipsoid, or sorry, an ellipse on a screen-aligned ellipse that's basically tracking the curvature of the display. And that'll actually improve the quality of this quite a bit. But I had an example of that, but I don't know where I put it. And anyway, so I went the simple path. So that's all I have for live examples. Let's see how much time I have left. Looks like I have about 15 minutes. And so I did want to provide a little bit of background. There was other things I really wanted to get to in this talk. Basically, I was going to talk about the environment I use. It's kind of like, I have like a version of Shader Toy, but it's kind of like a configurable thing. So, well, maybe I could show part of it on one of the examples. Let's see. Go back to the first example. So I didn't have a canned example for this, but this is probably going to look just like spaghetti code for most people. So what I have is I have a file here that I do all my work in, and basically it's just a giant shader. This is the original font program that I was showing on the screen. And so the shader, the file is basically, instead of having a bunch of files and then having to actually play around with loading a file, figuring out which one to modify, I just put like something in here that lets me know where my little subfiles are in one file. And then I have, at the beginning, I have a section of like I call it like a precompiled GLSL header, which is, it's not actually precompiled, it's just the GLSL I include before every other shader. And inside this, I define a bunch of functions which allow me to access resources. In this case, I'm actually using GL4. I'm using ARB bindless extension. And the idea there was ARB bindless was as close as I could get to accessing the binding model that I would get in Vulkan. But I don't, Vulkan's not ready yet. So what I do here on the top section here is I have a bunch of functions defined, and all the functions are basically they're all in my shorthand naming convention, impossible to understand. But these are basically functions that take a bunch of inputs and they write out commands. And so in my shader, I end up with this first shader here is actually a shader that writes commands into a command buffer. And I have a loop in my code, which is the engine itself is actually something like, let's see, how big is the engine? So the engine itself is about like 9.5, around, it's a little under 10K. And so when I say engine, I'm saying the engine, all it does is give me a bunch of tools I can use in a shader. And that's it. That's all I really want. And so in this shader, I basically write, the first shader I write a bunch of commands which sets up my pipeline. And it can set up what shaders I run. I can basically set up my textures. I can set up my resource bindings in my bindless handles. And then I basically create another shader which runs later, which can basically reconfigure the pipeline again. And so every 2 frames, I can reconfigure my pipeline. And that's the way I write my code. So I don't actually have to go into my C code. I actually don't have C code in this. It's in a different language I wrote. But I don't have to go to the original program and modify the program to actually iteratively edit and adjust my program. I just do that all in shader code. And so if I had another hour, we could go through all this stuff. But unfortunately, I don't. And I think I'd like to be able to take questions. So we have about 12 minutes left. So we'll start on the questions, if anybody has any.